to address that issue. So to address the issue with fixed global epsilon, so when you have one epsilon that applies to entire data set, you're going to run into the issue that we saw earlier. This epsilon cannot work for all the scenarios when you have different density areas, when you have areas with different density. Yeah, that's the accurate way to say that. So optics stands for ordering points to identify the clustering structure. It can also be seen as a hierarchical clustering algorithm. You're going to see why is that shortly. So optics produces a special order of the data points. It draw the data present the data in a graph that the graph can tell you where the clusters might lay. The graph can tell you what epsilons need to be selected in order to find the clusters as depicted in the graph. So in order to actually understand optics, we need a few more terminology. So earlier we have epsilon, and now we're going to define epsilon prime. It's called core distance. Core distance for an object P, this object must be a core point for it to have core distance. If P is not a core, then epsilon prime is not defined for this observation or this object. So this graph shows us another concept called reachability distance. Optics actually graphs the reachability distance for each every point. The reachability distance graph is going to tell you how to cluster the data points. So we need to define what reachability distance is. It's the core, it's the map, it's either the core distance of Q or the distance from that point to Q, whoever is larger. So in this example, the reachable distance to object Q1 from P, Q1 and P has a distance which is smaller than epsilon prime. Therefore, the reachability of to object Q1 from P is actual epsilon prime. If we have this Q2, the distance between Q2 and P is greater than epsilon prime, then the reachability is this distance. So it's either the core distance of this P or the real distance from the data point to this core point, if this distance is greater than the core distance. We're going to see why is that, why it's preferable to define it this way. It could actually be defined as the real distance, but later on we're going to see, we're going to show that it's preferable to not represent all those little details, because the points surrounding P, very close points surrounding P, they fulfill this epsilon prime, making P a core point. So anything within this epsilon prime area should be clustered together. We don't need to care about the little difference, subtle differences. We should just use E prime to represent the distance. If a point's distance to Q is actually greater than its core area, then we care how far away. It might be a point that's an outlier. It might be a border point. So later on when we see graphs, this epsilon going to make the graph much easier to read. Okay, so I think this at this time you probably are still kind of why do we need to know that? How do we apply those? So I'm going to run this animation. I mean, hand-controlled animation. So with reachability and core distance in mind, and we can start to look at this example. We have this data set. It's a two-dimensional data set with, I have 30 minutes, 16 points. So we still set an epsilon, and this is not epsilon prime. This is epsilon. In optics, we can set a greater epsilon. This optics will not be sensitive to this epsilon, as you're going to see why shortly. Then we set the midpoint to be 3. There is a storage area called seed list. We're going to, our data points are here. We're going to select a certain data points that's within the epsilon distance neighbor into the seed list. We're going to process those seed list through process those points by reading the points of the seed list. So let's see, we first select the A randomly as our starting point. So we will look at its epsilon neighbor and find that B and I are within the neighbor. So we put B and I into this seed list. And here we also add the reachability distance from A to B. And this is the final reachability graph that we're going to produce. So at this point, we only put A here. A, because it's the first point, there's nothing it can reach from. So therefore, its reachability is infinite. So next, we're going to actually process the next data points on this seed list, so which is B. We're going to add B. So here what we see, the core distance is the distance that's going to make A core point. So this distance covers 1, 2, 3 points in the A's neighborhood. Okay. So because this point is within this core distance, therefore it's the reachability distance is core distance 40. So next, we're going to process B. So we're going to plot B here with reachability distance of 40. So it's going to become here. It's a bar here. Let's go to next page, next slides. So we put B here. B becomes our core. And we find another data point within B's core distance. So we add C here. So every time we add points here, we sort this and according to the reachability distance to the current core. So to the current core, which is B. So we have I and C here, and next we're going to process I. We put I here and then draw a circle around I. We put I there. When we draw a circle around I, we can see its core distance is much reduced. K, L, J is within the core distance, so we use its core distance 20 here. Oh, L is not actually. L is further away, so we use its real distance. And again, we sort this reachability distance according to the current core I. And we add more. J going to be added next. After that, we're going to add L, M, and everything else. So what we see here, we set a fixed epsilon, but we can see I, J, L, K, M, K, NPR, this many actually are closer than 44. And even these two are closer than 44. We can now adjust our epsilon. See, if we set epsilon here, we're going to have two clusters. So the reachability distance graph show you the cluster by showing you the valleys. Every valley represent a cluster. So if we actually use 44 as our epsilon, then we have one cluster. All the data point is in one cluster. If we reduce it to this point, then we have two clusters. And their outliers can also be detected. So we can see A is an outlier. If we actually have a lower, let's see 40 epsilon, the effective epsilon here, then this A going to be an outlier because it's distant from all its neighbors. Okay, do I have questions on the optics algorithm or how this reachability distance graph is plotted?
I had a question. So when on the previous couple of slides where we had I as the center of our, why did we reduce our core distance? Why isn't it the same? So that, to me at that time, we should have had J, K, L, M, R all be as added in, but we only added J and K.
We added MR is here.
Was that at that iteration, or because you said the core distance got reduced, and that's what confused me, why we reduced it versus
core distance is reduced, but these are all within its epsilon.
Okay, so we consider everything in epsilon.
Yes.
Anyway, what is the significance of core distance being reduced? What's the difference between core distance and epsilons?
The core distance will define the distance between this core to anything within its neighbor.
So why are we reducing that?
That's a very good question. So this graph can probably illustrate some of the ideas. So we reduce this to 40, this is 20. When you have a graph, when you're actually not using core distance, here you're going to have variations, right? You're not using the core distance, you're using the real distance between the core point to its near neighbors within its epsilon prime neighborhood. You're going to have lots of zigzags, little valley, little mountain here. And it will make the final graph very hard to read. So using the core distance, you actually have smoother things that you can interpret to find the values and see the hills more clearly.
So is the core distance essentially like from I, because the size was set to, for min apps, the size was set to 3. Sorry, min points, not min apps. Since min points is set to 3,
right,
then the core distance is the smallest value that can capture 3 points. So I, J, and K, starting from I, so including I, we can get a 3-point neighborhood if we set it down to 20, so the core distance drops to 20. Is that
right? So you can see in this graph, in the final graph, you're going to know that these points are closer together than those points because we adjust the core distance.
I have a question.
Yes.
Go back to I, like point I, for example. In the seed list, why do I see point C as well?
Why do we still have point C?
Yes.
C was added in the previous step. It was pushed back because now with I in the center, we need to sort the reachability distance. We want to plot the points that's closer to I first.
So in here we should see K, J, L, M, R,
and the previous points,
I see.
points that we added before.
Okay. But we don't see the core point itself. Okay.
Yeah, does that make sense? So the idea is we want to plot closer points together to create that valley.
So is the seed list the points that are not explored yet as potential cores, but we think might be useful?
We don't know yet, yes. So at this point, C was processed here. After all those being processed, we come back to C. C is not an outlier. So here we note A, B, H are outliers, but not C. C is closer to this group. It's not distant from both sides. It's only distant from this graph, this cluster. It is totally close to this group of data points. It's just after we plotted all those clustered points, then we come back to C and find another cluster.
Here in why, so how do you, or why do you say C is close to, for example, D or F, but it's far from P or R?
We know the reachability from D to C is this much. So we know that C and D are close.
Okay.
And also D is very close to others. It creates a valley. So this C is part of this valley.
Do we know how much is the reachability from P to C?
We know the reachability from P to C is this much.
Oh, okay.
Yeah.
So all of this, sorry.
Go ahead.
Oh, sorry. All of this is based on, did you say earlier that it's based on calculating a distance, so similarity matrix?
Reachability distance. It's all based on the computation of this definition. Yeah, it's always helpful to go back. So this is a reachability definition. The idea is we wanted to find how close the other points to the current points. So reachability distance from reachability distance to object Q from P. We got to be very careful with the terminology here, because you can only from a core point is this much. But within its epsilon prime neighborhood, we will consider this to be reachability of all its close neighbors, because differentiate any of those differences doesn't make any sense. It doesn't offer any more information. If it's close, if P is a core point, then anything it's directly reachable things will be part of its cluster. We only need to know that its distance is not larger than epsilon prime. That's good enough. That would allow us to plot a smooth graph.
In this graph, isn't the height of C that bar the distance from A? Because that's when we added it in our initial circle. So it's not the distance from
because
P.
every time when we process a new points, our reachability are updated. Those reachability is updated according to the current point. So those values, those reachability distance are updated along the way, not the original distance.
But it seems like compared to P, C would be much further away because it's, you know, since the initial point was, it was about 40 from B, so just intuitively, it seems like it would be higher. Or maybe I'm missing something.
I'm trying to find an example here. J, okay, so I is 40, C is 40. So L here is 31, right? When we processing I. When we start to processing J, L becomes 19. So it's closer. So the idea is to process any points that's closer to the current point so that we can actually, if you recall the dbSCAN, the propagation process, that we add the nearest points to the current cluster. We are adding the nearest point to the current cluster. Therefore, we want to recalculate the distance. Maybe 40 was not updated very correctly, but the idea is to update the reachability distance so that the closer points will be all put together in one value.
Thank you. So it doesn't matter if it goes beyond epsilon or whatever the value is, we keep up, the idea is to keep updating it and keep reordering it till we kind of touch all the points.
Right, right.
Thank you.
So when the seeds point is exhausted, then we pick another points. Then this point is going to have, again, a reachability of really high. So that defines a new cluster. So here are some examples that we can see some of the features.
I have another question.
Can we finish this section? We're pretty tight on time. I only have 17 minutes, 13 minutes to go through this. I will be happy to answer your question after this, after the lecture. Sorry about this. So in this example, we'll see there's a very tight cluster and we see very low reachability distance. You look at the depth of this green part, this is very tight, relatively to green and the blue part. And we can also see some of the things here. If we actually cut a line here and lots of those points going to become outliers. You can look at the simulation. It's a YouTube video demonstration. We won't have time to look at it in class. I think this is a summary of, so idea is, I think we have all made the previous point. The idea of using optics is that you can actually not using a fixed epsilon. You can use an initial epsilon to plot out this graph and then using different epsilon threshold to cut this graph and find clusters. I think we should also, yes, have this example to show how it might work in a hierarchical clustering manner. When we actually put our line here, then almost all the points going to be considered in one cluster. If we cut our line here, we're going to have 1, 2, 3 clusters. you could actually have look at every one of those, and the larger cluster actually contains three smaller clusters. That can help you to create a hierarchical clustering structure. Some additional graphs to give you intuition what kind of graph going to correspond to the original data points. So here we have pink, and we have two clusters, the pink cluster 1 and 2. We have two red clusters, the valley, have lots of noise here, and a cluster in light blue. So sometimes the graph is not very easy to read. For example, in this case, you don't know where the clusters are. So it's not it's not all good.